If I have one charge, there's going to be a electric field, 1 point charge. If I have 2 point charges, then I'm going to add the electric field due to this charge and the second charge. If I have 4, then I need to add all the 4. But instead of point charges, if I had a distribution of charges, what do we mean by that? That means there's no one charge, 1 point here, 1 point here, 1 point here, 1 point here. Instead of not discrete in space, if it is continuous in space, instead of discrete, if it's continuous, then it's going to be a distribution of charges in a region of space. That means instead of 1 point here, 1 point here, 1 point here, and 1 point here, what I'm going to have is a distribution of charges now. Imagine a wire like that. Imagine a wire, not just a point, a wire. Then I can have some charge here, I can have some charge here, right? So this charge is kind of continuously distributed along this wire rather than at discrete locations like this. So that is called as a distribution of charges. How do you describe them? You describe them in terms of density. So human body or mass, you know, the density is mass per unit volume. Mass per unit volume, yeah, kg per meter cube. Similar to that here, density, charge is going to be Coulomb, and density can be per meter cube, or can be per meter square, or can be per meter. So we're going to be seeing 3 kinds of charge density, 3 kinds of charge density. This is volume, because it's per meter cube. This is surface, because it's per meter square, per area. And this is line charge density. Now let's look at the line charge density. For the first, we're going to look at line charge density. That means it has a certain dq over dl, that much Coulomb per meter. And the symbol that you use is called as rho L, rho with a subscript L. Rho with a subscript L. Imagine this line to be that distribution of charges. It is having the charge density rho as a function of r. That means whatever location that r is, the value of the charge density there might be a function of that position in space. The total charge within is, this is in Coulomb per meter, times the line element dl. So Coulomb per meter times meter is going to be coulombs. That is going to be the total charge. If you know volume density of an object, how do you find the mass? You multiply the density with the volume, right? You multiply the density with the volume, right? Similarly, here, the line density, you're multiplying the line density with the line length. Line charge density times the line length. That gives the total charge. What advantage does it give me? Gives me the advantage that, so instead of the electric field at this point due to each individual charge, I'm going to add this, and this. Instead of adding these 4 terms, now I need to know the electric field here, right? I'm going to break this into a small section of having a charge dq, a small little charge dq. What is the electric field due to this guy? The small electric field due to that guy. Then I'm going to add on each of those charges. That is what we are capturing here. There is a small charge dq, a small charge dq. Small charge dq. What is the electric field due to that charge here? Is the small de. That means after that, I need to do for this dq, how much is it? For this dq, for this dq, for this dq, so on and so forth, right? I need to keep adding them, isn't it? But this dq is changing along dl, isn't it? And that dl is so small that the summation becomes an integration. The dq is so small that the summation becomes an integration. Now let's focus on just the electric field due to dq. It's going to be 1 over 4 pi epsilon naught, the charge dq, because that's the charge in the small section, over r square, where r is the distance between the charge and the point of observation, the destination, and in the direction of r hat. This is by the Coulomb's law. So you got this guy here, where dE is due to dq, and notice that this dq from here, this dq is simply rho L dl, because rho L is the charge density of that many coulombs per meter times the length dl is going to be the small charge dq. So this is coulomb per meter and this is meter. dl being that small little section, yeah, dl between this small little physical section, the length of it is dl. How much of charge it is? Charge density times the length, charge density times the length, that gives you dq. So because of the small little charge, I got the small little electric field. But then as I move along the wire, I have all these other small little charges that are adding up. So that becomes an integration. So my total electric field then becomes a line integral. It becomes a line integral of 1 over r square rho L r hat dl. Rho L over r square r hat dl.